This is the general transformer where we are having two windings, winding 1 and winding 2. Okay. Winding 1 is consisting of n1 number of turns. Winding 2 is consisting of n2 number of turns. Okay. What is happening? This is called as core of transformer. Whenever there is a two-limb transformer, it is called as core type transformer. Depending on the design of core, there are two types of transformer. One is called as core type, another is shade type. There are three limbs. Okay. The winding is wound on the central limb. One winding, the another winding, two terminals. And it is made up of steel stampings. Stamping is of such size. There are a number of C-shaped stamping, C and I-shaped stamping, right? This is I-shape and this is C-shape. And they are connected together to form the core. And the core is of magnetic material. Now this type of transformer is having the complete flux inside the core. There is a little leakage. Little leakage in the flux, but here there is more leakage in the flux. Okay. Now if I am having these two windings and if I apply here V1 voltage, please remember I have to apply the AC voltage there. If I apply the V1 voltage in this direction, there is a production of flux within this core. I mean, whenever there is flow of current I, there is a coil. Okay. This is a coil, and whenever I am applying voltage, current I starts flowing. I call this current as the instantaneous current, where the current is in time domain. So we call it as Im cos omega t or sin omega. Normally, engineers are preferring cos omega t waveform because of its own advantages. So I of t, I am giving the time dependent current to this particular transformer winding. Whenever the current is flowing through the winding, as per the thumb rule, there is production of induced EMF within this winding. I call this induced EMF as E1. If I say E1 small e, it is instantaneous induced EMF produced. Now depending on the waveform, I call it as EM. Suppose I say it is cos omega t, I will just refer the waveform same only. I will tell you how the transformation is going to happen in the current and voltage. That is 90-degree transformation. I will modify this waveform later on. But at this moment, I am giving the voltage V of t. Because of V of t, this is Vm sin omega t, let us say. So I am giving this waveform Vm sin omega t. Because of this, the I of t is flowing, and the magnitude of Im is dependent on the voltage magnitude Vm as well as the impedance of this winding. I call the impedance of this winding as Z1, that is primary winding voltage, primary winding impedance. So let us define it. It is R1 plus J times X1. Z1 is the complete impedance offered or opposition offered by the winding to the flow of current. Okay, and this opposition is, if I calculate the DC opposition to this winding, to the flow of current, it is the resistance R1 which is opposing. If I want to calculate the total opposition to the winding because of its frequency dependent supply, then there is forming the reactance of the winding X1. If the frequency of the supply is 0, then this X1 will be 0 and Z1 will be called as R1 plus J times X1. I am defining this in Cartesian form or the complex number. If I want to define it in normal form, I mean polar form, it is Z at an angle phi. In some cases we call it as Z at an angle theta. Now this theta or the phi, that is called as the power factor angle, is dependent on the proportion of resistance R1 and X1. How much resistance is there within X1? Proportion of R1 in impedance Z1, proportion of X1 in impedance Z1 will decide the angle phi. We will go to that point later on. But at this moment I want to tell you something interesting, that there is production of flux. Please do not confuse between this phi and this phi. This is the flux waveform phi m. So let us try to draw it first. Suppose I want to draw the waveform. This is time t. I am giving you a view of the waveform. Okay. This is Vn, and there is a this is time dependent waveform. Okay. There is a flow of current. As I am giving the input voltage to the inductive side, you will find that there is a lagging waveform happening here. So let us say it is lagging by some angle. I call this angle as theta, that I defined here. It is the proportion of resistance R1 and X1 within this impedance. So we can start this waveform from this point. At this point it may be different. So let us say it is at this point it is coming. Okay, and the waveform is like this. You will find that this is the current waveform. This is IM, the maximum of this waveform. You will find that this waveform is lagging behind the some angle because of inductive circuit. Okay, and normally in the case of transformer, whatever the flux is produced will be in the same size of the waveform. That is, the flux produced will be of same nature. This is time dependent phi of t. I call it as phi m. Now, as the flux is having rate of change within it, there is production of induced EMF within this coil. That induced EMF is called as self-induced EMF. E1 is called as now the self-induced EMF is there and the current is flowing. It is getting magnetized. As the core is getting magnetized, after some instant you will find that it is getting linked with the secondary coil. This is the primary coil, in some cases it is secondary coil. Now on this side it is secondary coil. Secondary coil is getting linked with the flux because of this core. The core is magnetized and on the magnetized core there is a winding, and that winding is facing the rate of change of flux linking with the winding, and hence there is production of induced EMF within the secondary winding. We call it as self-induced EMF E2. That is the secondary winding voltage. Now what is happening if the transformer is not loaded? That is, this is open circuit. Okay, secondary is open. In this case you will find that there is only establishment of voltage V1. In this winding there is establishment of E2. Sorry, this is V2. Establishment of voltage V2 on the other side. As there is no flow of current, as the circuit is open, you will find that there is nothing happening within because of this output. And output is there only V2. It means I can say that if the transformer is on open circuit, it is taking the current on the primary side. This current is producing E1 and flux phi 1, it is getting magnetized, and that magnetized flux is getting linked with the secondary coil. There is production of induced EMF, self-induced EMF E2. There is production of the terminal voltage V2. Of course, this V2 and E2 are different because of the impedance of secondary winding. Now secondary winding is also having the impedance as Z2 equal to R2 plus J times X2. R2 is the resistance of winding, secondary winding. X2 is the reactance offered by the secondary winding because of its inductance as well as the input supply. You will find that if I vary this input voltage V, E1 will vary. If I vary this input voltage, if I increase this V1, I will increase, and this E1 will increase, E2 will increase, and V2 will also increase. There is certain limit on this. Now whenever the circuit is open, there is nothing connected to the transformer secondary side, and you will find that the current flowing to this is called as the no load current I0. In some cases, if you go for the books from the eastern side of India, that is Dharmadhikari University, you will find the current is called as magnetizing current I1. In some cases, it is called as I0 also, and that's why I have not shown here I1. But as soon as you connect the load there, suppose there are lamps connected within your home, and this load is variable because you are just varying the switches within your room and everything. You will find that as soon as the load is getting increased, the flow of current will start, and I call this current as I2. Now certainly this I2 is being supplied primarily by the input voltage V1 only, and hence this current is getting changed to I1. I call it as, in some cases, I2 dash. I will tell you how it is I2 dash. And now whenever the current is flowing through the secondary side of transformer, it is getting reflected within the primary side because this current will try to disturb the flux within the air gap or within the core, because whenever the secondary current is flowing, it will also try to establish its own flux, and that flux will be disturbing the total flux within the transformer, and hence there is disturbance of this E1, and whenever there is disturbance of E1, you will find that current here initially it was I0, now it has changed to I1. It means I can say that I1 is having two components. One is called as I0 plus the current which is flowing from secondary side, but it is reflected on primary side, and that current is called as I2 dash. Now this is the primary current. It means primary current I1 is having two components. One is called as magnetizing component, other is called as the component because of the loading on transformer, which is getting reflected on this side. Now what is the general transformation ratio? I call the transformer is having its power balancing equation. Power balancing equation. And that equation is V1 I1 equal to V2 I2. I am just writing the absolute values. Okay. You will find that if I want to calculate the current I1, then it is simple. That is V2 upon V1 into I2. Okay. And whenever I want to define this V2 upon V1, in transformer it is called as the transformation ratio K times I2. So henceforth I will not write V2 upon V1, but it is K. If I want to define V2 upon V1, it is I1 upon I2 equal to K. Normally transformation ratio is always less than 1. If I refer the secondary side voltage V2 as the lower voltage. Okay. Now this is the general mathematics of transformer. But as soon as you define any vector quantity, I have to define the waveforms. So let us try to draw the vector diagram of this transformer.